Hello guys, today we're gonna first talk about the permutation. What's permutation? We know the identity matrix, something like this. Only in the diagonals, all the elements are 0 and are 1, and then the rest of are 0. That's our identity matrix. And permutation just make the order of those rows altered or changed. For instance, if we have a 2 by 2 matrix, and that's our identity matrix, and then we just change it to, so we can see that the order of the row 1 changed to the row 2, and then the row 2 changed to the row 1. So why we use permutation? It's easy because in the last session we talked about LU equals to A. That is, any invertible matrix can be decomposed by a lower triangle and the upper triangle matrix. All right. But if we get a matrix something like this, 1, 2, 3, in that diagonals there's a 0. So how we can really make it right, then there'll be some difficulties if we just want to make it a L and U. The thing is that we can add a permutation here. So we make sure to change the row of the A and then make all the elements in that diagonals non-zero, so it can be easily decomposed by a L and a U. Okay, so here we want to change the row 1 and row 2, so it can be something like 2, 3, and 0, 1. So how we can change it? We just focus on the I, and if we change the I to a permutation, let's also change the row 1 and row 2 of our identity matrix. So we get a permutation like this, and then, okay. So now let's calculate what's the result. First will be 2 and 3 and 0, 1. So by calculation, we can know that if we want to change the row, specific row, we just add a permutation, and the permutation also with reference to the I, it also change the row 1 and the row 2. It will leave our A, that the matrix also change the row 1 and row 2, so yield this result. So, and if we get this, it will be easier for us to compose it by a lower and upper triangle matrix. And aside from it, let's just mention something very interesting about the permutation. For instance, let's say now we can have a permutation of 3 by 3, and then there's something like this. P multiplied by the PT, that's the transpose, will equals to I. So first we will get the transpose of PT. The transpose just change the row and the column. So here is 1, still the 1 and 0. Yeah, and then we change. So it will be actually in this case it will be the same as the PT. And then let's just calculate. Here is PT, here's P. Let's just calculate if it equals to the I. 1, 1, and the other are 0. Why it is like that? Actually, it can be easily figured out since PT, there's only one element in each row and in each column, and always the first row will multiply by the first column, and then exactly always the same elements in the row or in the column will be multiplied, so it will give us a number. And for the rest of it, let's say this by this and this by this, it will always be 0 because the number of 0 always multiplied by the 1. So we cannot get anything. So that's why it's always we can get the P and the transpose of P where equals to I. And then since P also, if always it's invertible, so always we can get the P inverse matrix here is always I. So what we can get here is the PT, always the transpose always equals to the inverse matrix of P. So that's something very interesting. We talk about the permutation. And then let's go to the talk a little bit more about the transpose. So the transpose simply is just exchange the row and the column. So here we have, it's not just, we can give a very random matrix, and the transpose of it, we can have just change. First is 1, and then let's change to the row, let's change to the row, also let's change to the row. So the transpose of it will be something like this. And let's talk about a case of R equals to RT. This has a name called symmetric matrix. So it means that if we create something like this, 1, 2, 3, and we have to make sure that it's symmetric. So, right, reference to the diagonals, we just get something like this. And then this is symmetric, right? It's very easy to visualize something like this. So it's matrix. And however, another conclusion we will draw here is that the any matrix here is, if we multiply by its compose, it always yield to a symmetric matrix. So we have example here already, and then let's just calculate it below. Okay. This is a 3 by 2, and here the transpose of it, it will be 2 by 3. So what we got here is a 3 by 3 matrix. And let's just calculate. It will be 10, 11, 7, and this will be 11, 13, 11. Here it will be 7, 11, 17. So we can see that it's symmetric. So why it is like that? So what we have to do is to say that any R the matrix times is RT. So always, yes, let's say the transpose of it, what will be it? As we see that this equals to the RT, T times RT, right? So this is R times RT. So from the simple one, we can see that equation that R, the transpose of RRT will again be R multiplied by the RT. So it means that any matrix who is multiplied by its transpose will be a symmetric matrix. All right. And now let's jump to the vector space. So what's the vector space, right? I mean, literally it just means a space of vectors, means a lot of vectors here. And to be more specific, if we have a vector view and a vector W, let's say to make it simple, those vectors, and of course, that's two vectors, but what's the space for these vectors? We can see that there are two operations, the addition and the multiplication. If we use view v multiplied by the k w. And if we do the two operations, it still falls in the space. We can see that, okay, it's linear. Or in other words, the two, any operations to make a new vector should fall in the vector space. So obviously we can see that R2 is a vector space, and then we can draw something here. The 2 and 3, it might be something like this, and then the 1 E might be something like this. And if we just do anything about the V and W, for instance, right? Everything, all the two operations, the plus and the multiplication, the addition and multiplication, it always will fall under the R2. So that's a vector space. And another point very important is that it can be multiplied by anything, means that even 0 W. So the 0, 0 should always fall into this vector space. If not, it's not a vector space, right? So we have to really take account of the 0, 0, the 0 vectors. So what is not a vector space? For instance, only this part of the R2 is not a vector space. Why? Because if we use minus V minus W, that is right, we use -1 times V plus -1 times W. So this will just fall here. And this will not be a vector space because this is not included in these areas. It cannot be closed. We should just use any numbers here and here to multiply by the view and the W. And it should fall in the same vector space, but it doesn't fall there. So this part is not a vector space. So as we can see that the one quarter of a space of R2 cannot be a vector space because the linear combination of the two vectors, it will not really fall exactly into it. However, there's some subvector space that we can still find in the R2. For instance, we can find a line across the origin. So if the W and the V are two vectors on it, we can really figure out that any linear combination of the view and W always will fall on the line. And also the other thing important is that, right, it includes our 0, 0, the origin vectors. So that's a subspace in the R2 that is also a vector space. And how about the other thing? Even a smaller one, then a line will be just a 0, 0 vectors. Why is like that? If W equals to 0, 0, V equals to 0, 0, any linear combination by the two operations, multiplication and addition, are always add out to 0, 0. So 0, 0 is also, even though it's a small, but it's also a vector space. So from this, we can really lead towards the R3. So what's the question is what's the vector space of our R3 and the subvector space, okay? Vector space. The first is 0, 0, 0, as we say in the 2, right? It's the smallest vector space in R3, and also R3 is the ceiling, is the bigger one. So, and in between, we can see that if there's a plane that cross the origin, the 0, 0, 0, it can also be a vector space. And we can also imagine that if there's any line that cross the 0, 0, 0, it can also be a subvector space. So we can see that any plane cross origin, any line cross origin, the R3 itself and 0, 0, 0, that's the vector space or the subvector space of the R3. All right. We have talked about the vector space and then we have a matrix. So, right, I mean, this is like a composed of two vectors. The first one is 1, 2, 4, and the other one is 3, 3, 1. And now we just use another terms to describe the vector space for a column space, because we have to figure out, okay, what's the space can really include all the combinations, linear combinations of the two columns. So we give it a symbol like say A. What's the column space for the A matrix? And if we just draw something here, right, it should falls under the R3 or something like that. Maybe 1, 2, 6 is something like this, and 3, 3, 1 is something like this. So now we have to think all the linear combination of, right, we just gave it a name, V and W, or the linear combination of V and W. So what will be the shape of it? If we really imagine it, it will not really occupy the whole R3, but it will be a plane. And this plane definitely will cross the origin of it. So that's exactly the column space of A. So that's what we got. Since we have already know the column space, so we should use this to think of a matrix, something like this. A 4 by 3 matrix. And the question is that if we have A, X equals to B, this one always have the solution of X. So it's means that if we can just figure out to have any X that, or we can have any B here, right? B will equals to B1, B2, B3, B4. We can find any combinations of B1 to B4, and then we can with any combination of B1 to B4, we can find X here. Well, we can really, right, make it a column space or the vector space. X1, X2, X3. So there's 3 vector space, and and this means there's a linear combination of the 2 column space, and then we want to get any combination of B1, B2, B3, and B4. First thing is, this is a R4, right? It has 4 elements in the vectors, so it should fall into the R4 space. But the question is that can really any combination of it will really, I mean, to fill all the R4 space? Actually, it cannot, because there's only 3 vectors. And those 3 vectors cannot really fill all the R4 space here. And in another terms, it's like we cannot assume in that B1 to B4 they will belong to the R4 space, and we cannot find exactly the x1, x2, x3 to satisfy the condition that any vectors in the R4 can be found. So that's how we really analyze it in the terms of the vector space or the column space. So I have put the questions here. The first question again, given B can be any, combination of elements in the R4, is the equation AX equals to B always be solved? The answer is no, because because the 3 column space cannot really fill the whole R4. So definitely we cannot find any combination of B. Okay, and the second question is that, so we know that we cannot really have any, combination of B's there, then what kind of B's can be solved this equation? Well, it's simple, since we have already something like 1, 2, 3, 4, 1, 1, 1, 1, and 2, 3, 4, 5, by x1, x2, x3. So if the B will be 1, 2, 3, 4, then it means that the x1 equals to 1, x2 equals to what? 0, x3 equals to 0. So if with 1, 0, 0, we can really, we can solve it. And of course, we can, if the B equals to 1, 2, 3, 4, we can find that x equals to the 1, 0, 0. It really can solve the equation. And the other thing, of course, if for the B equals to 1, 1, 1, 1, then we have to get x equals to 0, 1, 2. And in another case, if for the B equals to 2, 3, 4, 5, then we can find x equals to 2, 0, 0, 1. So in other words, only if the B can be the linear combination of this, the equation can be solved. And that's our second question. The third question is, can we throw away one column? Because here we got the 3 column vectors, and can we throw away any one of them? The answer is yes. Why? Because 1, 2, 3, 4 plus 1, 1, 1, 1 equals to 2, 3, 4, 5. So we already have the linear combination of the previous 2 columns. We can get out the third last column. This one doesn't really contribute to any of our equation, because from the first one and the second one we can already get. And in other words, it's like if we get this one and this one, we don't even need the first column, because from the second one, the third one, we already can describe this vector space or the column space already. As above, we talk about the AX equals to B, this equation, and we figure out, okay, the B cannot really be any combinations in the R4, because we only have a matrix of 4 by 3, so it cannot fill, right? Any X multiplied by A will not really fill the R4. B definitely cannot be any combination that R4. All right, and then let's talk about another non-space. And we need make the B fixed to 0, 0, 0, 0, and 4, 0, and we just talk about if X can form sort of vector space. The first thing we have to consider is the arrangement. So if x1, so if x equals to 0, 0, 0, of course, it will automatically equals to the 0, 0, 0, 0. So the arrangement is included in the in this. And if we just try something more, we can find out maybe something like 1, 1 minus 1. It also can make this equation equals to 0, 0, 0, 0. But it's not the only solution. We can have like 2, 2 minus 2, or any k, k minus k. It can give us the solution of this equation. So the question is that, have we found the vector space? Exactly, yes. In the R3 of X, it can be a line across the origins, right? Something like that. So that's really the vector space of X. And back to this one, can we find a 1, 2, 3, 4? Right, earlier we have 1, 2, 3, 4. Can we find any X or vector space of X that with Ax equals to 1, 2, 3, 4? The answer is no. Why? Very simple. If X equals to 0, 0, 0, it doesn't really fall in the vector space, because if X equals to 0, 0, 0, the function will Ax will equals to 0, 0, 0, 0. So the function cannot be solved. So definitely there's no vector space for this X if we get the B equals to 1, 2, 3, 4. All right, I think that's today, and the next session we'll really dive more into the non-space and the X equals to B, the vector space. All right.